So I want to welcome everybody to the Chat with Chip about the Propeller 2 webinar. Briefly, we have a very loose agenda. So first introduction, you're talking to Ken, and also on board here is Chip and Jeff.
Hello.
And hey, Jeff, and a whole bunch of the community, which is the most important part because they got us here. I already covered how to make comments, ask questions. So Chip's going to talk about the P2. Towards the end, I'll talk about where we are with the hardware. And you can ask questions throughout the entire webinar, or you can hold them to the end. And we'll try to keep Chip moving. So that being said, I'm going to stop sharing my screen and pass it over to Chip.
Can you guys see me okay?
Yes.
Okay. All right. Well, for anyone who's here that doesn't know much about the chip, I'll just do a very brief overview. I'm going to share my screen here. Let's see. Okay, you should see a picture of the chip. Is it there?
Yeah.
Mm-hmm.
Okay, so this is the Propeller 2 chip. It has eight cogs or 8 cores in it. It has 512K bytes of hub memory. Each cog has 4K of RAM split across 2 dual port memories. And this chip is very easy to hook up. If you look at this, you'll notice, I don't know if you can see all the detail, but there are no ground pins on this chip. There is one giant pad on the back side of the chip, which all grounds go to, kind of like a star ground configuration. And what you have on the outside are the VDD pins, which you power the core with at 1.8 volts. And then for every 4 I/O pins, you have a unique VIO pin, which should be set to 3.3 volts. So on our demo board, we have for every 2 of those, or every 8 IOs, we have a single load dropout regulator, which is very quiet and has good decoupling on it. So every set of 8 pins get a very quiet power supply. The only other pins on the chip is there's 64 I/O pins, which are where everything goes through. And then there are 4 special pins. Down in the lower right corner, you see XI and XO. You can hang a crystal right across those 2 pins. There are internal loading caps in the chip, so it can swing a 20 megahertz crystal or higher, or even down to 5, no problem. It's kind of designed to run at 20 megahertz, but you can go above or below that. The other 2 pins of interest are up in the upper left corner. There's the test pin, which for everything we do is just going to be tied low. The foundry uses that to test the die. They pull it high, and there's a bunch of JTAG channels that appear on the I/O pins. But for our purposes, we keep that low. And then pin 100, the last pin, is the reset pin. That's an active low input. It does not have a pull-up, so you need to pull that up on your board. And then during boot, the 2 pins next to that, P63 and P62, can have a serial conversation with the host if some pull-ups are configured on the pins just below. And the documentation gets into that. In fact, I'm showing you this picture out of the documentation, which will, maybe Ken, you can put a link to. Most people, I'm sure, are familiar with that. But anyway, so you just have 64 I/O pins, 2 crystal pins, and a reset pin. And then you have the power pins.
Chip, we had a question. Should there be a bypass cap on every VIO pin?
It wouldn't hurt. It wouldn't hurt at all. It's good to have the thing pretty well bypassed. This chip was actually really way over designed. We thought it was going to take about 2.5 watts. So it has a massive power grid on the chip, and then every 4 IOs have their own power supply, and there are 4 VDD inputs per side of the chip. So there's 16 total VDD inputs. Internally on the die, jumping to the lower ground pad, there are 16 VSS connections, which go to ground, and then there are also 16 GIO connections, which feed the IO pins. So this thing's really, it's designed to be really well bypassed, but fortunately it wound up taking a lot less power than we thought it would. And in the end, we added clock gating into the design, so for a lot of uses, the power is half of what it was on the Rev A, and I'm talking about the Rev B silicon. So the part really doesn't get that hot, but it's designed to wick heat away very efficiently and receive high current power supplies, you know, and bring them onto the chip with very low local drop on the die. Okay, so that's the chip itself. It's designed to be pretty easy to use. Just got power, ground, and your IO pins and crystal pin and reset. and everything that you want to do is going to be happening over those 64 IOs that are numbered P0 through P63. Okay, so let me close this thing or get it off.
Any questions for Chip while he leaves this image behind?
Okay, just for showing on this webinar, and it's, let's see, let me get into it here. Okay, it's not much. If I assemble this, it becomes, let's see, let me go down. Just this data, it's less than a kilobyte. It's about 0.7 kbytes of code. So this program here, this is it. There's nothing else that runs in the chip. When you download this code to it, there are two DO or two CC divided by 4. I don't know what that's going to be, but that's how many longs there are, basically how many instructions there are in this program. No other code runs, just this. And when I download this code, I hit F11. All right, now let me switch to my camera. Okay.
Now we see you.
Yeah.
Okay, you can see me now.
Yes.
Okay, so anyway, what this program does is it performs a Fourier transform, and the code for that is right here. So it basically just takes one pin. You see this microphone. This couples into one of the I/O pins just with a coupling cap. There's no analog front end or anything. So every I/O pin has an A to D and several DAC modes. And right now the A to D is enabled for this one pin, and it's at 100x magnification. So that means 33 millivolts is full scale from, saturating from 0 to all ones. And it's a sigma delta or delta sigma bit stream that comes out of the ADC. So anyway, it's very sensitive. It just takes this mic signal and it gets a nice, full scale waveform out of it. And so what this program's doing is it's taking that one pin bit stream, and it's using a smart pin which attaches to every pin, and it's doing a 14-bit sync to conversion. And I think right here, yeah, see where we select 13, this sets up the analog to digital conversion. So these 3 lines here are all that's required to set it up. The first one, the right pin.
We can't see your code.
Oh yeah.
You're sharing your video.
Oops, let me go here. Share screen. Back to this. I think this is it. Can you see the code now?
Yes.
Okay. So here, this right pin in these upper bits here selects A to D. This selects 100x magnification right here, these 3 bits. And then this here sets up the sync to mode. And then it does a right X pin to tell it what resolution to go to. So 13 is actually 14-bit resolution, and then it enables the pin. So that's all you got to do to start up on a pin, automatic A to D conversions that report through the in signal from the pin whenever they're done. So what this thing does is it waits for a sample, and then it gets it and it sticks it into a buffer and then scrolls that buffer. So all it does is I think 30 kilohertz, it's like 30.3 kilohertz. It grabs signals or A to D conversions, puts them into a buffer, and that's all it does. So this is a cog doing this. I could have put this on an interrupt. This is a very low bandwidth, but I just have a whole cog doing this now. Then over here, this program periodically grabs that. First thing it does right here is it waits for the video screen to refresh. So if we go down to the bottom here, this is all it takes right here. See this code? This generates an HDMI screen, a 640 by 480 bits, and it's using actually Luma 8. Let me fix that. Which is a mode that doesn't require a palette. It just takes 8 bits for a pixel and then applies some RGB coloring to it. And those 8 bits become intensity. So it generates the screen over and over. But each time it's done with the visible portion, it does this. It writes a byte to location 0. It writes a 1 to 0. So this thing up here that does the spectrograph, it waits right here. It waits for the screen to refresh so that it can go and redo the bitmap without any visible glitch on the display. And then it scrolls the entire screen and inserts new samples at the end. And that's it. Now here's the heart of the thing. This is the Fourier transform. Some of you are familiar with this. What a Fourier transform does is it converts a set of samples in time into frequencies over that period. And so if this is a 1024 point FFT, there are going to be 512 frequency bins from DC to 511 over 512 of the Nyquist limit. And through a very strange process called these butterflies, which is a computational kind of fix. See, normally this process would take, for 1,000 points, it'd take 1,000 times 1,000. It'd take 1,000,000 operations, but now it takes n log n. So it's 1,024 times the log base 2 of 1024, which is 10. So it only takes 10,000 operations. So it's 100 times faster than the raw algorithm would be. So here we do, right here is the FFT. This code comprises the entire FFT. And for anyone who cares, it uses the Cordic. Normally, at this point of the loop, we calculate, an FFT would normally calculate sine and cosines using a reverse lookup here. And we did that right here. This line here actually does the bit reversal. So there's no need for a lookup table or anything. That's just a 2-clock instruction. So it does that. And then here in the loop, it uses sine and cosine, or excuse me, the angle that was going to generate the sine and cosine to rotate the actual values with scale. So all in one whack, it does the job of looking up the sine and cosine and scaling a value by both of those separately. So it does one value, does another, and then it picks up the results of the first which calls rotation, and then picks up the second rotation, does a little add and subtract math and loops. And in the end, it converts those things to powers. And so we use another Cordic instruction here, which Q vector A1, A2, these are both signed 32-bit values. This thing works at full scale. The Cordic goes all the way to 32 bits signed. And so what that does is it takes A1, A2, which are a Cartesian coordinate pair, and converts them to rho and theta. So out here pops the get QX gives you the rho, which is the power, and the get QY would give you the angle, which is a nice big 32-bit angle that rolls over when it's all ones. That's like 359.99999 something degrees. And then when it rolls to 0, that becomes 0 degrees. So you don't have to worry about any kind of funny carryover or stuff that you might otherwise have to do if you're dealing with radians or degrees. This is just pure, simple binary. It works real nicely.
Chip, question for you.
Yep.
So people watching the chat are asking about the programming language, and we explained how it's parallax assembly, and they're asking at which point would they be able to do this with C or Python or Spin?
Okay, yeah, so sorry, I didn't explain
your
this.
Workflow.
Right, okay, I'm using my own tool, which is Peanut, which will later become the Spin compiler. So I'm still working in assembly language. I've just about got Spin running. It's kind of running, but it's not integrated yet, and I have some other things I need to do to it. But we already have some tools that are made by some forum members, like Eric Smith made a thing called FlexGUI, which actually can take his anticipation of Spin2 or C or BASIC, and there's a few other things. He also even made a Python executor. Anyway, you can use his tool right now to write full code. I'm just using my little assembly language tool, which will become also the Spin compiler because I'm familiar with it. And also, Ross H. on the forum made a C compiler that he calls Catalina, which covers both Prop 1 and Prop 2. But here I'm working in assembly, so it's very direct and right to the hardware. Anyway, so this is this program. It's not big. You can see it's about 0.7 kbytes. So now I'll switch over to the video. Let's see here. Stop the share. And okay, you can see in the background here, right? So what it's doing is a live spectrograph. That's the result of this program I just showed you. So it's 0.7 K of code with nothing else, no libraries, running directly on the chip. It's using 3 cogs. Could do with probably 2, maybe even probably 2 cogs. but it's running on 3 just for simplicity. And it's doing a live Fourier transform just over and over and over of the sliding window of samples that are coming from the microphone. So what you're seeing on this screen here, and let me change over to the other camera so we can get a closer up look at it. Okay, let's see, maybe I can set this thing right here. I want you to see the detail. Now, it doesn't want to focus that close, but I think I can put it here. All right. Okay, so as I talk, this whole camera and screen setup aren't doing this justice. When I run this on my main monitor, it looks beautiful. It's nice and rich, but you see a lot. You see everything that you hear. So you can see on here, as I talk, I'm creating all kinds of spectral phenomena. And you can see how there are lines partitioning things. That's actually my glottal pulse and all of the harmonics that are being shaped by my vocal tract.
So somebody asked, can you whistle a sine wave?
I wish I could whistle, but okay, I'll try. Here we go. Huh. Okay, I can't do that, but I've got something maybe even better than that. I've got the function generator set up here. It's doing a basically like DC to 15 kilohertz sweep, right? So let me turn that on so you can hear that. Now I'll put the microphone in front of this. Now look. Okay, so you get the idea.
Wow.
It's just listening and showing you spectrally what's happening as each little window of time flies by. And I can change this to log sweep.
People like this, Chip. They have a question. FFT makes it possible to do live audio encoding to MP3. Is that right?
Yeah, I should enable all kinds of stuff. Yeah, if that's what's required to do MP3, we should be able to do that easily. And that's only audio band. It really shouldn't be that demanding at all. So anyway, this is just kind of a simple demonstration of how it doesn't, take a whole lot of code to make something, and how the Cordic makes things that might otherwise be just about impossible really simple. One thing, if you look at this, there's a lot to learn by playing around with this program. And I'm going to zip up everything I'm showing today in a zip file, and I'll put it on the forum after this. So if anyone wants to get it and load it and play with it, you can do that. For this thing, I'm using the HDMI board on pins. It's in the code. It's set up for pin 48. And then I have the audio video board, which is this thing with the microphone plugged into it. Whoops. Can you see where the mic plugs in? Anyway, kind of interest, you think about speech. This is why speech is so complex and why your brain has so much to listen to. If you look at speech on a scope, the waveform reveals almost nothing to your brain. But when you see spectral activity over time, it becomes very meaningful. Like this, if I make an S sound, here's an SH sound. This is what your brain understands as it hears it. Anyway, so that's a little spectrum analyzer that is only not very much code. Ken, are there any questions about any of this?
A question about PNet. This might be best answered by Jeff. Will it have a serial terminal display to interact with the P2?
Yeah, we haven't talked about that, but we did intend to, at the very least, update the propeller tool, which does have a serial terminal, to support this. And then we intend to work on a multi-platform tool afterwards that will be, similar to propeller tool. I'm not sure. We haven't really had some major discussions about that yet, but we definitely do want a serial terminal available.
And then Dennis asked Chip, what version of PNet did Chip use to compile this code? He couldn't get the FFT code to compile 32K.
Yeah, okay. I'm going to put it in the zip. It's let's see, if I go to my little thing here.
You don't have to zip it up now.
No, I'm changing this thing every day, so it's always in flux. But I call it 33L, but it's really beyond that. I just haven't output it yet, so I haven't revved it. But I'll rev it and put it in the zip. Now, I do see some questions here. Someone asked, is it going to be possible are we going to make libraries to encapsulate a lot of smart pin functions? Yeah, of course we'll do that. And, they'll at least be available for spin. And we'll also have, heck, we could make FFTs, whatever's of interest, whatever's useful, we'll build. And once we get that whole thing working, it's going to be very easy to add functionality. I've really been waiting to get spin up and running, because once it's there, all these things I'm showing you, I could start with little effort mixed together on the same chip and be running, if I wanted to, several different monitors, all kinds of feedback loops and inputs, and it wouldn't be a problem. But right now I have to mix everything kind of by hand in assembly. But we're just about to get around that problem.
So there's some other questions that relate to the hardware itself. One was, are all the pins and functionality accessible on the evaluation board?
Yeah, every single pin is brought out without encumbrance on the evaluation board. The only thing that has anything attached to it are pins 62 and 63. Those are the serial I/O pins. And then some of the pins that will hook to the 8-pin flash chip. But that flash chip won't do anything if it's not getting a chip select signal. So all the other pins though. So I think the top 6 pins have potential. They're actually connected to other things, which are usually silent. But the other 58 pins are completely free. There's nothing connected. They're just brought out right to the connector.
Okay. And with ground underneath, what does that mean for us when building our own boards and hand soldering this? Okay,
what you can do, we did at first, was just put a big hole, a metal lined hole, maybe 0.1 inches wide, or maybe how many millimeters would that be? 2.5 millimeters, so that you can stick a soldering iron tip down into there, and then wet the back of the chip, and then solder it to the metal lined hole. That's a fine way to deal with it if you're hand building something.
Okay. And what actually made it to the ROM for the production device?
Everything that's been in the chip all along. So there's Peter Jakaki's Tacos, his 4th engine is in there, and then also there's an SD booter that Ray wrote, or that's Clouseau 99. And he also wrote a little monitor program that's in there that you can invoke by, I think, Control D from the, we don't really have the docs updated for that yet. I need to get in there and do that. But I'm sure Peter has stuff to explain that when you log into the chip, just hit escape and you can go right into Tacos, or Control D will take you into the monitor that Ray wrote.
Somebody asked, what is the minimum sampling window possible given the butterfly approach and, say, a 240 megahertz base clock speed for this FFT?
Okay. So it sounds like you're wondering what's the performance of the FFT. In this case, this is, ask again if I didn't get it right, but if you're asking about how long does it take, this thing is running at, let's see, what am I clocking? It's at 250 megahertz because I'm outputting to HDMI. So it's taking just a hair over 3 milliseconds to do a 1024 point transform. So that's, again, about 10,000 instructions. So it's about, and 3 milliseconds at 250 megahertz is what, 750,000 clocks divided by 10K is about 75 clocks per operation. And that could actually be improved. If you look at the FFT right here, this business here could be pipelined. And right now we're feeding 2 instructions into, we're putting them into the Cordic and getting them out a little bit later, but you could load that thing up. I'll have another program I'll show you which completely stuffs that pipe. And so every 8 clocks, you can introduce a new command to the Cordic and you can get old results out. So if this thing were to be rewritten, because the way this works is you're sequentially scanning through samples. You see this here, and this here, you're reading and writing.
We're
That
not
could
seeing
be,
your code.
oh yeah, sorry. Let's see here. There we go. So what you see down here, these reads and writes, these are sequential. It's loading in two variables or coordinate pair working on them. Well, you could load in 16 coordinate pairs and work on them, and you could probably speed. I was thinking the other day, right now we're about 75 clocks per operation. You could probably get it down to about 30 or so. So you could make it take 1.25 millisecond. And other things, other approaches might be possible too to speed it up. I don't know. This is just some quick code I wrote. This whole FFT here is only 79 instructions, including the conversion to power at the end and the thing that reads in samples at the beginning.
He says that's exactly what he was asking. Excellent, close enough for a transient measurement to satisfy pretty much any FFT need. 3 milliseconds is already really good for 1024 points.
Yeah, and if you want to do something smaller like 256, well, that'd be 256 log base 2 of 256, which is 8. That would only take, what, 2,000 instructions, 2,000 operations? It should be 5 times faster. So 1/4 the points, but 1/5 the, is that right? 5 times the speed, or 1/5 the time. Yeah.
Okay.
So we'll, in the end, we'll have libraries to do these kinds of things, and we'll make it very, very easy to use from Spin.
So here's another totally different question, which I think is an excellent one to talk about. The P1 has a 512 byte cog RAM limit. I understand that the PT removes this limitation somehow. Is that true, and how complicated is that in code?
So, okay, it's not what you think. It's actually 2 separate memories. So it's still a base register memory of 512 longs, but now there's an additional memory called the lookup table RAM, which I'm actually, let me go back to my, let's see, let me share my screen again. Or wait, share screen. Here we go. So if you look right here, if we do a set Q2 and a read long, this is actually reading in. It's actually filling the LUT all with 2 instructions. Read 512 longs into that thing, and that'll take basically 512 clocks plus about 8 of overhead. And so that's just to read and write. You also have a read LUT, write LUT instruction, which I don't know if we have at work in this program. Oh, here we go. Here's a place where we're reading it. So what we do is we read in the scan line from the bitmap right here. Then we get the power sample. And then, oh, and here, this is kind of important. We scale it and we clamp it. FLE, force less than or equal. This keeps it from going over 8 bits, causing crazy looking stuff if it overflows on the screen. So that clamps it to full intensity. And then here, we actually read in the last long that contains the last 3 bytes of the scan line, and then which has been shifted, scrolled by 1, and then we insert into it right here. Whoops. We insert the byte, then we write it back. So we read it, insert the byte of interest, write it back, and it's done. And then here we boom, push the whole thing out back to hub memory where the bitmap HDMI generator, the thing that generates the video frame, picks it up and displays it. It's funny, as I was writing this, normally when you program, you got to pick up a byte, do something with it, put it somewhere else. This goes on and on. But with these kinds of instructions where you can do big operations all at once, it's actually so fast. And see, the way I'm scrolling this thing is I read it. Let's see, where do I do this? I read it at 1 byte shy. Excuse me, no, wait. Let's see, where does this stuff happen where I actually write it back? Write long, I2. Let's see.
Well, Chip looks over his code. If you want to now, since we're about halfway through this, raise your hand with any audio questions. You can do that too. I don't know if Chip has other demos to show us, but will tell us.
Yeah, go. I'm open for any question. Anyway, I'm not thinking straight. I'm a little nervous and on the spot here, but it basically picks it up at a byte, at a 1 byte offset, where it can then insert the new sample into the end, and then it writes it back to memory, effectively scrolling all those bytes in hub RAM, but just kind of incidental with the move. Now,
Chip, we got a question too from Paul Voss.
Yeah.
Hi, how are you guys? That's amazing. I just had a question. I'm not a programmer by trade, and so I'm very familiar with the P1 and spin. Done a little bit of assembly, but not nearly at the level that you're doing here. Would you have advice and about say someone has a nice spin library, a lot of stuff running in spin over 10 years, and you just want to fire this thing up? Is it ready for people like us, or do we need to hold off for a few more months as things get sort of worked out in terms of the compilers and all that kind of stuff?
Well, I think Eric Smith's tools, the Flex GUI, could probably compile mostly what you've already got, and he generates ASM code, so it's very fast.
Yeah,
I've
but you can ask with that. Sorry, I've experimented with that too, taking existing spin code. Of course, there are some things that you'll have to modify, but it really usually doesn't. It didn't take me very long to figure out, oh, I just need to tweak this or that. There were really minor changes, and then it just compiled and ran.
Mm-hmm. So I can get one of these evaluation boards from you and buy that, and then be up and running fairly easily in a general sense, if I'm familiar with a P1 and a lot of electronics and build a lot of stuff like that.
Yeah, I don't see why not.
Yeah, cool. What about documentation and stuff? And I apologize, I haven't been following all the forums, so I'm still feeling a little like an outsider in terms of just getting my head around all the amazing work you guys have done and what the state of the project is. And
well, we have a big document that if you go to our discussion forum, there's a sticky thread. I think it's called P2 Silicon or something, but it has a link to the current documentation. And right now the documentation's 104 pages.
Okay.
But the only thing it's not detailing yet is how the debug scheme works and how what all goes on with the booter ROM and what's possible, with
and
the
Paul, Chip lives on the forums really well. That's his development environment. But we also have everything on propeller.parallax.com.
Yeah. So I think I just have to make the dive and start playing with this thing because it looks really cool.
And Paul makes some really neat CNC controller hardware.
Oh, awesome. Yeah, this thing should be a dream for anyone doing motion control where you got to set up feedback loops. And I mean, if you look at this thing here, so I'm talking and you can see it responding, right?
Yeah.
This is so simple that there's nothing going on here. There's no operating system. There's no heat management.
Yeah.
There's no garbage collection. Everything that normally stalls real-time processes on a big machine doesn't exist in this because there's just no need for it. So when you make something that works, it just keeps working that way. It's not going to blow up because some other app got installed or something happened or it's just having a bad day. It's going to run like you'd want it to.
Yeah, I have a question along those lines really quick, and then I want to leave it to other people to talk here. But that's the reason I love this propeller chip is it's just, I'm sort of working with the bare code. I'm not using a lot of libraries. I'm coding everything. It does exactly what I want it to do. I can go in, I build these CNC foam cutters and stuff for aeronautics. And, you go into a classroom and you just set it up. It works every single time. There's never, a key serve issue or some other stupid thing. It's such a breath of fresh air to get off of the, sort of where we've gotten to with, sort of operating systems and licenses and all this stuff that just makes things so unreliable these days. But
unreliable and no fun, yeah.
And no fun, and you can't get control of it. You really can't. It's all blocked. So anyway, it's so great. Has there ever been a thought of sort of creating a compiler based on the on the propeller chip, so you could just completely ditch the laptop or computer and be independent of all this, like, it's like quicksand with, anytime you get something working, a couple of years later, it doesn't work anymore on regular computers, and it'd be nice to just have a very reliable way to program these things.
Yeah, that's been my long-term interest, is getting off of and out of the mothership of everything else, which is always, like you say, it destroys all your efforts and time. And I hate making the investment to make something nice just to have it all screwed up later on for no cause of my own. And so I'm really interested in making something that will actually kind of respect my efforts and not just destroy them in time. And so the chip's capable of hosting and doing everything. All we really need is some someone up there I see asked about a multi SD object. Yeah, we need that so we can read and write files. So once we have those things set up, it's going to be pretty easy to do that. And also, you're working on the chip. You can plug a monitor into a few pins, and you can have fantastic real-time debugging that is lightning quick. Has no discernible delay or anything. It's super responsive, and we can make a debugger that works like that too, which you're never going to quite achieve on a PC. Yeah, and I'm thinking for what you guys do with education too. I'm in education. I teach in engineering at Smith College, and it's just a constant nightmare. Every time you get something working, a year or two later, it doesn't work. Smith has even talked about stopping support for the PCs and going to Chromebooks with the students. I mean, it's just a disaster. And if you could go into a school and say, here's a complete set, you get the box out, this will work, the students can program, they can run these things, they don't need anything else. That would be amazing. Yeah, I would love that. Thanks, because, the problem with all this stuff and the way it works today is it's so burdened and so contingent on so many things that are only half under your control that it's fatiguing on the brain, and it's not conducive to actually developing anything and making anything new, because it's beating you down the whole time you're trying to get ahead. And it's a killjoy, and it doesn't respect you. And so if you get something that is not only reliable, but it's lickety split, you hit a button and your code runs in a split second and you see the effects of your change, then your brain is able to be many times more effective because you're not waiting around for stuff. Even if you got to wait 5 seconds for something to configure and download and program a chip, it's enough time for your brain to wander and you get off track, and it kills your productivity. But if you could be 100% on all the time because the tool and the system that you're working on are not, yanking the carpet out from under you every 5 seconds, it'd be way better. That's what I look forward to.
So Chip, I have to keep moving you on. Thanks so much, Paul.
Thank you. Yes.
All right, Chip, can you demonstrate any more capabilities of the P2 right now?
Yeah, let's see here. So we could do just about any kind of a video format, right? So let's say I have something.
I think
here.
I saw like a bird image on an HD display, and then also
lots of
while
birds.
you prep that, what's the resolution of the ADC and the DAC?
So it goes up to I measure it to be about 14 bits. Someone the other day said it was about 13. They did some virtual instrument setup with it, but I've gotten like what I consider 14-bit response out of it, where it's stable at 14 bits, and that takes about 8,000 clocks to get a sample of that quality. So it's not super fast, but if you want to do like audio stuff, you can get way better performance, because we have a Sync 3 conversion in the Smart Pin, which actually doubles the effective number of bits. So, theoretically with that thing in 256 clocks, you can get a 16-bit conversion. But I've noticed it's not quite there. Sync 3 is very good at capturing signal dynamics, but it's really not much better when it comes to DC. But if you're looking at live signals that are changing quickly, then the Sync 3 conversion works really well.
Perfect. Okay, you're going to show something.
Okay, yeah, so let me switch cameras here real quick.
I'm trying to get these questions answered for you all. They're streaming in faster than we can handle them.
Okay, so here you see, I'm going to tilt this, but what we have here, is a, it's in portrait mode, but it's a big HD, it's a it's an HDTV being driven by component video, right? But check this out. Oh, by the way, the code for this thing, this is a cheesy way to show you the code, but let's see here.
You could share that screen.
It's very small, but there's not much to it. You see this? Let me see how big it is. So the code that displays this, oh, wait, there's a monstrous, okay, the image was taken out. So look at this. It's not even, the program is not even 256 bytes. It's not even a quarter K. And it's generating this HD TV screen here. So
let's see that screen.
Here's
too.
the working code. Anyway, so you go over here, right? And it's actually what you see, this monochrome image is a single pin off the chip. It's in 75 ohm mode, and it outputs 2 volts. So when the TV clamps it with another 75 ohms, it drops to 1 volt peak. And so it's just this. See, if I pull this thing off, let's see, try to get both in the view. Pull this thing out, signal goes away. Plug it back in, signal comes back on. So that's 1 pin monochrome. Now if I plug these other 2 signals in, oh, that's the wrong one. See, it doesn't. No. Okay, let me put this in. So there we go. Now,
nice.
Yep. So that's just 3 pins off the chip and 1 cog generating 1080p HDTV signal using YPBPR mode, just component video. So the green is the Luma, and then the other 2 are the color channels. So component's great. It's only 3 pins. HDMI takes 8, and there's some speed limitations with it. So we don't signal fast enough to do, we'd have to be going at 1.48 gigahertz to signal this in HDMI, but we can signal it in analog over 3 pins, no problem using component.
Okay, Chip, a few more questions. Could we do buffered SPI with the smart pins?
Buffered SPI, let me think. Sure. Well, wait a minute. Okay, so the smart pin can reel in data that comes in with a clock, but you're going to have to, every time a word comes in, you're going to have some code that makes the decision about what to do with it or how to react to it. So what it does, the smart pins take away the highest bandwidth problem for you and then leave the next level for assembly language. And then above that, you can have, say, spin code, you know, dealing with the highest level results of everything.
Okay, and can you summarize briefly the streamer, what it does, how it's used, and then also put your video back on you if you want to.
Okay, so yeah, so the streamer, let's see here. The
and
streamer,
also, go ahead, Chip, sorry.
Okay, it's just what it sounds like. It's a circuit that's in every cog. So each of the 8 processors have this thing, and it can pull data to or into or out of the main hub memory at 32. So every cog has a FIFO that interfaces to the hub memory, so that whether you're executing code in hub or you're using the streamer, it can get all the data it needs, or it can write all the data it has without any kind of miss occurring. And so it's just a state machine that you, let me share my screen, and I'll just show you a code that makes it go. Whoops, let's see. This is it, I think. Okay, whoops. Okay, so here, let's see. Uh-oh, I think I have a window open somewhere. Let's see, my program here is kind of hung because I think there's something else that's wanting some attention. Oh, yeah, okay, here we go. Anyway, this X continue instruction here, can you see that?
Yes.
That's a streamer command. So if we look at down here at M880, it was calling out this thing, this configuration word. So this is the command right here, which just says, you know, send out some literal data and do it for 880 ticks. And a tick is set up by the streamer has its own NCO. And so right here, the streamer is being set to actually half the clock rate. It says clock rate, but that's half the clock rate. So and how fast are we running here? Okay, we're running at 297 megahertz. Yeah, so that would make sense. So some of these comments aren't accurate. I'll clean this up before I put it up. But anyway, so the thing's running at 297 megahertz, and every other clock, it's outputting a pixel at 148.5 megahertz. So you just feed the streamer commands. Like, see, these are many X streamer continue, continue, continue. So you'll kind of until you receive the next command, and then it automatically goes. But you can go off if you know you have time. If you've given that thing, it'll buffer 2 commands. If you've given it a big command, you can go off and do other things. And then when you get back into an X command, it'll wait until it's ready to take it. Then it'll let you go. And you can also set up an interrupt that tells you when it's empty. So you could actually drive all this video from interrupt code. It's very simple to do. And that way you can actually have your mainline code doing something totally different, because the streamer commands are only required periodically to keep things going.
Chip, another question. Does the current P2 eval package, the silicon footprint and thermal profile, along with the planned upcoming form factors, have any different or enhanced thermal environmental limitations as compared to the P1?
Okay, so does the chip have any different thermal characteristics?
Thermal or environmental limitations as compared to the P1?
No, it should be much better, actually. Now, environmental, I think that's probably equivalent, but as far as thermal goes, this is a special package that we're using from Amcor, and it's designed to very efficiently wick heat away from the die and carry it out to a circuit board, which has a big via array underneath the chip, and goes out to some maybe 2-ounce copper. So this package we're using has a theta J A of like 22 degrees C per watt, which is super low. That's very low thermal impedance, whereas the propeller 1 would get hot, but there was no means in the package to efficiently get that heat out. Whereas this thing, the die goes right down to your circuit board, and a ground plane will dissipate the heat. Can I show some? Go ahead.
Oh, what were you going to say?
Nothing.
If you have another demo.
Yeah, I've got. You see this on the screen here?
Yes.
Okay, so this is every pin has an A to D, right? And it also has a little like a windowing sample filter, so it can take those zeros and ones that are coming out and then run them through a big shift register that has weights on each tap, and each clock it sums those together. But we found some really cool ways, so we didn't actually have to sum every bit tap up every clock. We used like an integral approach where it automatically adds stuff coming and then subtracts it going out. So the math was actually pretty trivial to do this. But anyway, we have these windowed filter functions so that a pin can actually report an 8-bit sample anytime you want to request a sample from it by using these window shift filters. So going along with that, the streamer has a mode where it can grab 4 pins worth of samples at once, which is 32 bits, right? So a byte each from 4 consecutive pins, and then store it right into memory for you at whatever sample rate you want, because it doesn't matter when, the sample's always ready. You don't have to respect any kind of sampling boundary. Anyway, this is meant for an oscilloscope. See, if you can see that little white line right there, that's showing the trigger. So it's triggering off of this channel. The trigger is set to, like, it arms here and triggers up there. And that's why the registration is constant, because that was the trigger point where it stopped the capture and then went back so many samples to where the trigger occurred. So it's FMing, it's synthesizing like a sine wave, triangle wave, sawtooth, and square wave, and then triggering off this, but just showing, and then there's a little bit of persistence here. You can see it kind of fades away as it moves. Anyway, so this thing can actually act as like a 4-channel oscilloscope.
And
Chip,
the only will the programming amateurs like myself, the mortals, be able to use this easily?
Yeah, because we'll have objects to do this for you from spin or wherever. And you'll just set up some trigger condition. And now in the future, I want to redo this thing. I want to make the A to D in the chip a lot better so that it actually generates about 4 bits per clock, so that we can get, in 16 clocks, we can get a solid 8-bit sample, and have a mode where we don't have an analog front end, because this is good for audio. It's kind of luxurious, but it only has a bandwidth of a couple megahertz, and then it poops out. It starts rolling off. But if I can build a simpler converter or a mode within the ADC to do a lot harsher conversion, where it actually kind of uses just a resistor balance and beats against the incoming signal, and does it 4 at a time with different offsets, so we can get 4 bits per, and we'll be able to get super good, right up to Nyquist changes with good gradients on any I/O pin. And I want to make it a background feature so that while the chip is running, you can stick the A to D on all pins if you want, and it's just a background thing. It's not modal, so you don't have to put the pin in an ADC mode. You simply turn on the ADC for that pin, and it can log any phenomena that's going on with the pin.
There's a couple of questions that have been asked about minimum power. Is it similar to the P1? And is there a low power mode or sleep mode? How much current's required to maintain that?
Okay, so the quiescent current is pretty low. It's like a 30 microamps or something. But when you're running, I think at boot up, it starts off with like 31 milliamps. And if you're running all 8 cogs at like, the top end, I mean, I've got some things here that are running at 320 megahertz, and Peter Jakocki runs all day at 360 megahertz, but I think that might be pushing it. So I do my highest stuff at 320, but at 320 megahertz, all 8 cogs running, when all the smart pins going, all the FIFOs going, we seem to get the current consumption up to around, I might be wrong, someone can chime in. Was it like maybe 1 point, or no, maybe was it at 1.8 volts? I want to say it's like 800 milliamps or something, which is a lot, but the package is designed to take in several times that. I mean, the way we work the power and ground pins on the package and the super thick metal on the top of the die with a big power routing grid, it's designed to carry a lot more current than it needs and to get rid of a lot more heat than it generates. But you can burn, 1.5 watts or so.
Okay, Chip, can we spend one moment on housekeeping, then come back and enable more audio for people?
Yeah.
Okay. So very briefly, I'll just take control of things here. Okay, do you see the message about OBEX now?
Yes.
Okay, so just for information for everybody, we're closing down OBEX at some point. We've moved everything onto the Parallax GitHub so the community can use a tool that they know better, and that, yeah, you can issue pull requests. This is now working. And also about parts. So there are some questions about parts, what's available. Right now we have these in stock. These are 4 packs of chips. They're expensive at $100 for 4 pack. But we have limited quantities. We have 58 sets left, and our next delivery is arriving in April 2020, which is the purchase order we're planning on placing tomorrow. So for that purchase order, here's way more information than you want, but I'll tell you what it boils down to. If you are planning a product, like several have told us, over a dozen people, you have the opportunity to order what we call risk production parts. They are our final engineering sample. They come in trays of 90, and those trays are $1,080 each. You can order between 90 chips and 990 chips. This information is on the Parallax forums too. I would need your order. Tomorrow we're placing this order. If you don't order chips and you have a project, not to fret, we'll still have 3,000 to 5,000 units available around April. That should last us until September. Those units can be for our customers, can be for tools, for modules, things that we're making, but we generally will be very careful selling them out. So if you're actually doing a project and you already know you're using the P2, like some customers are who are developing in PASM, in parallel with chip, they're taking us up on this option. So if that's of interest to you, we need your order. The P2 evaluation board, you asked about these. We put about 250 of these out, and we're currently out of stock. We have another 100 units in production the last week of December. We're going to ship those around January 6, 7, 8. And you can go online right now and back order them. Just look for part number 64,000-ES, and there is also an accessory kit. And Carol Hazlitt was asking about the accessories. Can I use these things? At the moment, people are using them probably with Flex GUI and Eric Smith's tool and some assembly code from Chip, but there's not a lot of really easy to use spin resources yet. So that's all I wanted to share. And I'm going to stop the sharing now.
Okay, my question.
Yeah, please.
Yeah, it goes right in with what you're just talking about now. For us semi-literate programmers and sort of robotics hobbyists, are you going to take the PS2 further down, like making things like an PS2 activity board or PS2 Bobot or things like that a lot of us are used to using? And for backward compatibility, I've been finding the propeller to be almost infinite. I can even use Blockly Proc on my old Hydra board. So I like the idea of the backward compatibility.
Well, since you've been around for all these releases with us through the years, you kind of know how this goes. So things start out a little bit complicated before they become easy to use, and it's pretty much public what the progression here. But Chip has to get spin working, and then I think other tools will become easy, and eventually you'll see the educational products from us. We're looking closely at MicroPython, and you can use that right now. And it's an interesting design they're talking about where it could use spin running in different cogs to do some of the stuff Chip has shown. But we don't really have a solid plan in place for that, but it will progress that way. I mean, you're early to the party, you're an early adopter, and we're a small team these days, and also, quite honestly, low on funds. So it's going to take some time. We need the community. We need you and the other 90 plus people that are hanging out right now to help us out with all this. What would you say about that, Chip?
I'll be using PASM mostly for my stuff, PASM, because I do know assembly language. What was the other thing I had to ask? Oh, yeah, on your current products, like e-paper, the e-paper module and stuff like that, if I do the circuitry between the evaluation board and the end product, it'll still work with the PS2, right?
Chip?
Oh, wait.
Just make my own circuit.
Voltage level differences for communication between P2 and other 5-volt hardware we have?
Mm-hmm.
You know, okay, I was thinking about something else. I'm sorry, Carol, I didn't hear the last part of your question.
She's asking
if I take your current products,
yep,
like your different sensors and stuff like that, and make my own interface circuit to the evaluation board, would that still work with the PS2? Or will there be some...
You mean the propeller too? Will it still work with the propeller too?
With the evaluation board.
It should, as long as the interface is at 3.3 volts, it should all be fine. If you can get the code to signal properly, and yeah, it should be the same interface. Both the Prop 2 and Prop 1 are all 3.3 volts on the I/O.
Okay. Okay. You only have a few products that need 5 volts.
Yeah, less and less, it seems.
Yeah, some have been both voltage levels, but lately things have been more 3.3 here.
Yeah,
So,
go ahead.
Can I make a question?
Please.
I have a technical question. Imagine that since the power banks are being supplied separately, can I imagine that I do a project that I just want to use a couple of pins? can I just use the P2 with the cores on the one or two power bank, or one or two I/O banks supplied?
Yeah, well, you have.
Or
There are some things
yes,
you'll
yes.
have to hook power to. So the XI and XO pins work off of the pin 32. So VIO 32. What would be called 32 plus 3 would be 35. So you'd want to power that pin so that your clock circuitry will work, and then you'll want to power, I think, the first pin because that's what the reset and test uses. So the first and middle power pins you have to power. The others you actually could leave unpowered.
The first pin, let me see.
That would be V0003. Well,
Oh,
depending on,
I see.
yeah, you just need to make sure the XI and XO have power and the reset N and test N have power. So they're each fed by a local. And you know what? I'm really not exactly sure which one it is. I believe that I'm trying to remember where the power division is. Okay, I think.
Well, I have some confusion. I'm a bit confused because you said that I should power XI and XO.
Well, yeah, XI and XO are powered from either V2831 or V3235. Let me.
Oh, okay, I see.
Yeah,
so one of the I/O banks supply is also supplying the oscillator.
Right. Yeah. So that happens for each set of corner pins is stealing power from one of the adjacent V pins or VIO pins.
Okay. Another question. Is there any limit in size that we can use in the EPROM? Say that the program can have 512
Are you wondering,
K bits, right?
Oh, you're wondering if you could use a smaller, like 8-pin flash chip?
No, bigger.
Yeah, as long as
with the same space for programming, but so let's say that the second half is used to store data or something.
Sure. Yeah. See, the way these 8-pin flash chips work is they all take command 3, which means begin read. And so that's universal across all these chips. So if that's supported, it can start reading the boot data from the chip, and that's all that's required. So what would be potentially different is the software that downloads. So we'll have to do what we need to support a few different variances, because sometimes chips program differently, but they all start reading the same way. And so if that command 3 is supported, it can boot.
That's because what I was thinking. I don't know if you saw my posts lately. I'm thinking about doing a board that uses two P2 chips. But I wanted both chips to be programmed with the same interface, the same FTDI chip, and using the same memory, the same EEPROM chip. What I was thinking was one of the P2s was the master. That one was directly programmed by the FTDI and had direct access to the EEPROM chip, and the other was programmed by the first P2 chips. It would need some kind of bootstrap or something.
Yeah, you would just use the booting protocol. It's really simple. And if you look in the main document, if you go to the end of it, it talks about the booting protocol, and it's actually set up so that you can hook up a whole bunch of P2 chips on the same serial lines and talk to them individually based on how certain pins are wired. That you can choose.
Oh, nice. That's nice.
Yeah, so you give it a 64-bit mask and a 64-bit match pattern, and it looks for those I/O pins to read in those patterns with those sensitivities. And you can have separate conversations with each chip.
And Chip, I have another question from Jim Kuhlman. I just enabled his audio.
Hi, Chip. Just
Hi.
a real quick question. You talked about tidying up spin and releasing it. Do you have a rough estimate of when that would be available?
It could be in just a couple of weeks. It's just about done. I mean, it's kind of living now, but it's not integrated into the propeller tool yet. So I'm just going through adding the last few things I know. I would have probably had it done already, but I added multiple return values to the language, and that threw a lot of wrenches into things. So I'm getting, that had a lot of ripple effects. So I'm getting all that stuff straightened out now, and it's really not that far, and it's going to be really fun. It lets you, you know, it's easy like spin, but it also lets you load, if you want, assembly code into the lower registers, because it only begins at 167 hex on up. So 0 to 166 register space is all open for whatever you want to do. So you could load different programs in there. You can call them. They can be kind of like old DOS programs that are terminate stay resident, where they can actually start up a process and run on interrupts. And meanwhile, your spin code just runs along like normal. So you get a lot more use out of a cog.
I love it. I would say keep having fun for a while and don't hold yourself to a release date. Thank you.
It's getting close, yeah.
Thanks, Jim. Okay, we could have more questions. So let's see here. We have Michael Summer, and just enabled him to talk. Okay, try now, Michael.
Okay. Hi, Chip. Question. This is Mike or MS Robots. Question is how do you somehow cooperate with Eric and his spin 1.5 thing? So I mean, you put in that multiple return stuff, but Eric did a lot of nice things to spin and is porting it back to the P1. And how do you look at his stuff, or is there some cooperation?
Well, I actually don't know what all he's done. I understand that he took kind of an idea of what spin was slated to be at a certain time, and he implemented that and probably added a few, you know, some neat stuff into it. But I really don't know that it's the best that I can make it for the way it works. So my supposition is that once this is done, Eric will probably choose to adopt this so that a customer could take his.
Yeah, I'm pretty sure that he does. But are you corresponding with him, kind of talking to him once in a while, or?
Not really about this, no.
Because I think it's kind of complicated. I mean, he is doing a wonderful job there with that integrating of different languages, and it. You know, I think you are right. He will follow you. You can't do, but try to look at his stuff. It's pretty nice.
I've been using his MicroPython port too.
Yeah.
Yeah,
okay, that basically was kind of just the question is how, if and how you think about cooperation there, because it would be nice to have a bytecode interpreter and kind of being able to run it to say puzzle, you know.
Oh yeah, of course.
Nice. You know, it would be a nice combination when the same source code would run on systems.
Yep. Yeah, I think we'll get there. I don't mean to like ignore what he's doing right now, and I don't want to be pig-headed, but I've got like this long-term plan of where I want to go with spin, and I want to get to that point. And if Eric, you know, wants to support it, I think he will. I think it'll interest him to do so. But then the customer would have an option of, you know, doing development in our tool. But if they want to make things go a lot faster at possibly larger code, they could use his tool.
Yeah. That was my plan. I mean, thinking about that. I mean, even if 502 kilobyte 12, I mean, sounds big, but well,
Yeah, yeah, I can
in
get
your
even
memory, and you are down to, you know, the bytecode, spin bytecode is extremely important, I think.
yeah, it'll be compact,
Yeah,
but it won't be as fast as what he's made. But it'll be way faster than spin 1 at the same clock rate was.
yeah, sure, yeah.
Chip,
Okay.
got another question from Jonathan Shook. Thanks, Michael.
Hi, I maybe I missed it in the docs, but I was just curious what the maximum throughput for single channel digital communications would be, like for SPI or whatever. What's the best interface for that when you're pairing with other chips, and what is the best single channel throughput you can expect?
Well, let's see. The smart pin mode, you'd want to use the synchronous serial transceiver modes, right? And I am not sure really. We have some clock delays. There are some, you know, end cycle delays between inputting and outputting, and those could have effect on how quickly you can run that serial stuff. But I think Evan H on the forum has been experimenting with this. Also, I think Michael Summer, who just spoke, has also, and I think I've heard numbers from them like the main clock divided by 3, maybe 4.
Okay, that's significantly higher than what I was thinking I might need for the projects I've got in mind. So no worries there. I just wanted to confirm.
Okay, no problem.
Got a question from Ted Hunter. Yeah.
When you have a moment, I have one other thing I'd like to show.
Okay, let's take Ted's question, then we'll do that.
Good idea.
Ted, are you here?
I'll try.
Oh yeah, we got you now.
Audio. I'm just joined on an audio call. I'm in a moving vehicle. Sorry.
That's great.
Related to integrating assembly into a spin program. I read on the forum some time ago that there may be potential for a spin program to over and do some assembly and come back into spin to maybe help users get into assembly, because once you get into it, it's just so beautiful. Just wondering if there's a integration plan for that.
Yes, absolutely. Yeah. So spin, because the interpreter is not taking all the room like it used to, and it's designed to be, you can call out from the interpreter. So you could actually write assembly code that you can call from your spin interpreter, and you can even, like, I'm going to switch screens and just type up something, and I'll show you something. Let's see here. Share screen. Let me go back to this business. Okay, can you see my little screen here? So I'm going to make a pub called, oops, let me get here. Go, right? And this, let's say it has 3 inputs. It can have however many outputs you want. How about X, Y, Z? And then it can have local variables I, J, K, right? So this could be like the first line of a public. So what you can do is you can actually say, just within your pub, you can say, I'll tab out here, you can say org, and then you can, so at the end of it, you'll put an end and it will fall right out. So it's inline assembly, but here's what you get to do in there. The first 16 longs, you see how this is arranged, A, B, C, X, Y, Z, I, J, K? That actually takes, this is offset 0, offset 1, offset 2, offset 3, offset 4, offset 5, and then 6, 7, and 8 for these guys. So those are copied from, when you do some inline assembly, those get copied from the stack in HubRAM into 1E0 to 1EF registers. And then those names get temporarily applied to those registers. So you could say in assembly, you could say like add A, B, XOR B, A, C. And then you could, if you want to write those back to an output, you could say move, let's see, X is one of your first return value, right? you could say move X comma A, and then you could do a little integrated return right there. Boom. So that would actually add A and B, XOR it with C, and move it to the result, so that when this routine ended, it would kick it out as the result for X. So it's going to be really easy to do inline assembly. And the nice thing about the inline assembly is you get symbolic access to all of your little local, your parameters, your return values, and your locals, all just as simple registers at 1E0 to 1EF. So the assembler will put all that together. And you can also write code separately that you pull in, and it doesn't have awareness of your context like with local variables, but you can have programs that start up and do something or terminate and stay resident, run on interrupts thereafter. You could load them at any point. I could put org here. I could put, let's say I want this to come in at 100. I could do that. And so it wouldn't even bother what's in the beginning of memory.
Thanks very much. That's exciting.
Yeah, if you're in a car, you probably can't see any of that, huh?
No, I'm watching.
Oh, okay. Okay, good. Anyway, I'm really excited about Spin for this reason alone, is because it's going to be great to be able to put assembly right into your code, and it's going to open up a whole new world. It'll make it real easy to learn from Spin down to assembly, and it'll be a good stepping stone. It'll be less abstract than before.
Did you mention there was another demo?
Yeah. Let me see.
Okay, and while you prepare that, I still have hands up for Jonathan and Ted. Okay, so I think, Jonathan, you have a question?
Actually, my question was answered. Thank you.
Perfect, thanks.
All right, can you see my screen, or can you see me in the monitor here?
Yes.
Okay, so this is a little program. I'll show it to you in a sec. It's not even 100. It's like 120 and less than 120 instructions long. But what it does is it runs the Gorzel thing. You see this spot on the screen here? Oh, it's drifting. Let me calibrate.
And hopefully your Wi-Fi improves while you show this.
Oh, okay. So anyway, you see here we have this pattern here, right? So is that you, Ken?
That is cool. Yes, I've not seen this demo.
Ken hasn't seen that.
Oh, you never saw this.
This is so cool.
I thought you're being like a real salesman.
Yeah, I could do that too.
Okay, so anyway, the Gorzel engine, it's actually a streamer function, right? It's part of the streamer. It can output on 4 DAC channels 4 separate waveforms. So what we have here is this is like 0 degrees, 90, 180, 270, and then there's a pickup right here. So as you move your finger on this, it's outputting 600 kilohertz sine waves, right? And it's checking for coupling. It's listening on this pin with the Gorzel thing, which is kind of like a slice of a Fourier transform. So it's just continuously measuring. So if I go this way, it's coupling between these two more. If I go over here, it couples between these two. So see, that's the vertical. It's got, let me re-download. There's something shifty about this whole thing with being in front of the TV, but you can see my hand here. So it's not contacting, right? But my hand is this nice big capacitive kind of plug that floats around, and it variously couples these outer 4-phase rings to the center sense point. So this is kind of one application. I mean, you could do kind of gesture sensing with something like this. But if you run this thing in a closed loop mode, you can actually do, well, this is kind of closed loop mode, but let's say you're running through some transducers, right? You're outputting a phase locked signal and you're inputting it somewhere else. Well, you can measure the phase delta, which could show time of flight, aside from the amplitude, which would show what the signal strength is. So you could actually do sweeps through things. You could find out where the peaks are and determine where resonant points are. You could do all kinds of funny stuff. But this is like unexplored yet. This is just something I made, kind of you know, I made this thing thinking this ought to be possible.
I'd like to make that maybe on our laser cutter. Could we fabricate that as a tool to give to people as a demo?
Right, right. Yeah, well, we have this little board here, right? But we need to put more separation. We're redesigning it so that there's going to be a bigger gap, you know, around the sense pad and then the rings. So because this thing is just too persnickety, it's like it's not right.